I wanted to make a video of creating the equation and solving them for our exponential and logarithmic operations. So that way, just in case you needed to watch it again or weren't completely clear or maybe even missed class. So we're going to start with this one right here with the bacteria doubling every hour. What we saw when we were looking at exponential functions and scenarios were we were able to create this model, this exponential model, this equation that describes, right, how the bacteria are growing, right? The initial amount, our A, is the 3 bacteria cells that it starts. I'll say at the start, and right, starts with the 3 cells. And then our B, which is our rate of growth, right, is it doubles every hour. So that's where we get that 3 and the 2 in this equation here. What we also want to know is that X is our time in hours, and Y is our amount of bacteria. Oh. After that amount of time. So, right, if 1 hour passes, then we know that we'll have double 3 times 2 to the first power, or 6 bacteria. So what we can now see is that, well, if we want there to be 100 million cells, that's our Y, that's our amount. And so that's going to equal my 3 times 2 to the X. We can, now this is just like every, equation you've ever solved. Divide both sides by 3. We want to isolate the variable, right? Get X by itself. And we get 100 million divided by 3 equals 2 to the X. And if you want to write that as 33,333,333 and 0.3 repeating, you can, which we will in a second. But right now, and maybe we will write it like that right now, right? If we actually do that division. And so now this, again, either number, neither of them are very pretty, right? Either number is going to be this idea of 2 to the X. And so our question is, right? So what power do I raise 2 to get that 33 million, 33 and change million, right? And so we can do this in a couple of ways. What we learned this week when we're introducing logarithms is that the definition of a logarithm is to get that X out of the exponent. That's how we can undo the exponent. So what we can do, and I'm sorry, I just have these slides so you can see, I'm going to move over here, but I'm going to cross that out so it doesn't get confusing. We're going to have our 33,333,333 and 3/10 repeating equals our 2 to the X. And I left a space there on purpose because I'm going to change my color here. Let's use green. And so what we do to get that out of the exponent is we take the log and it's 2 to the X. So our exponent, the base of the exponent is 2, right? That's our B here. I can even call that our base. And so that's why we want log base 2. And that log base 2 is going to undo this exponent. So we're going to have log base 2 of our 33,333,333. Repeating, go back to blue. And then this is going to be, with our log properties, we move this x down in front. So this becomes x times the log base 2 of just 2. And so what then happens is this log base 2 of 2 is 1, right? It's what power do I raise 2 to get 2? Well, 2 to the first power. So this becomes 1. And so then we're left with log base 2 of 33,333,333.3 repeating equals x. Sorry, I should have moved that down a little bit. Wrong button. So I'll erase that 1 and I'll move this over here. This equals 1. And so now you can type this in the calculator. What you'll notice is that there is not a log 2 button. So you need to use the change of base formula. And so I can write that out. Let's see, do we have another color? Let's use orange. So you can have the log base 10 of 33,333,333.3 all divided by, maybe I'll keep it in orange, log base 10, nope, not of 2. And you can get that exact number, or that's where you can plug that into Desmos. And I'm going to do that here. I'll show you how to do that. And real quick, or you can use the change of base formula with the natural log, where it'd be the natural log of this number. And they mean the exact same thing. It's just whichever button you'd like to put. The natural log sometimes is used more often. Maybe so now let's take a look at Desmos. So I wanted to show us that we're just looking at this log base 2 function. And what we saw was that here, when we were looking at our exponential function, we had y equals 3 times 2 to the x. In this, right, our x was our time, our hours, and here our y was our amount. When we use this inverse function, the log function, our x now becomes, maybe I'll change the color here, change this one to red. I'm going to erase since we're in red here. Here we go. So here our x is now the amount and our y is the time. And what's happening is because in inverse functions, we're going to see after in the next couple of classes that what happens is we're switching the x and y, and we'll talk about what that means. But for now, we can see that in our inputs and outputs according to this log function. And what I want you to notice is that if x is the amount and we're looking for the time, well, I need that amount was 333 million. And so, or sorry, not 300, just 33 million. And so you can scroll all the way. But if you look here at 5, I'm only at 500 and I'm only at not quite 9, right? 8.966. So that could take a lot of scrolling. Another way to do that is, and here I'll close this out and I'll start anew. I'm going to move these down onto the screen so that way that's for the other ones. And I'll start here. So if we think about a table, then what we have is our X1 and it says Y1. So you can just start typing in stuff. But say you want to know, well, I I want to know what y is going to be. I don't want to figure it out. So you can literally type it in, log base 2 of x, and it's not just going to be x, but we got to define it as x, this to this sub 1, x1. And now you see the dots appeared. So as I start typing in, I can zoom in. Now I'm going to see the actual points on this line, right? 1, 2, 3, 4, 5. And so you can see it keeps going and it does the calculations for you. So you don't have to worry about it. But now, again, you can keep typing in numbers, or you don't have to go sequentially. We wanted to know what 33,333,333.3 repeating, right? And then we get, we don't have to follow this all the way out to that x value. We now have that y value here. So at that many, it would be about 25 hours. One other thing that we saw was, okay, you can see it in the graph, right? We can look at the X amount and we want to find Y as the time. We can then create a table to do that, or you can type it into Desmos as almost like a calculator, right? As a function. So log base 2 of our 33,333,333.333 repeating. And it's not showing up here, but you can see it just draws this horizontal line and it tells you y equals this number, about 25, or right, this 24.99. So I wanted to show you those steps in Desmos, and actually you can also use it like in Google. Oh, let me clear that. So we want, right, log base 2 log calculator of 33,333,333.333. All right, so sorry, Google didn't automatically calculate that for us, probably because it was a little bit more complicated, but this log base 2 calculator did. You can see that's our number and then that's our solution. The next thing, or let's use an actual calculator and you can see how the change of base formula works. And so now to show how Desmos, obviously a couple of clicks and you get that. You can find the same thing by using just the calculator on your phone. As you notice, what I want you to see is that the calculator only has the natural log or the log base 10. So that's where we use that change of base formula. So you can do your 33,333,333 and 3 repeating. Then you hit either button. If we'll do log base 10, then you divide it by 2 log base 10 and now hit enter. And now you see we have that exact number, about 25. We'll clear that and I'll do the same thing. 33,333,333 and 3 repeating. You can do that with the natural log, divide that by 2, the natural log, and then we get, again, the exact same number. So that's how you use the change of base formula, because we don't have the base 2, or sorry, log base 2 in our calculator.